Mike has been working at the Control Center for the Hubble Space Telescope for, I think, over 29 years or so, and he can tell us more specifically what that is. He's a senior systems engineer, works primarily with the fine guidance sensors, and he has a lot of experience, obviously, with the telescope. And he and I talked not too long ago about presenting a talk to skyscrapers about what he does there, how the control center works and so forth. I mean, many of us have seen articles written about the Hubble telescope. We've seen the pictures, obviously, but I don't think I've ever really seen too much about exactly how it works, how the communications work, what it takes to control it and point it and so forth. So I've been really looking forward to this. I'm excited to hear more about it, and really glad that we have an expert like Mike who has such experience with that. And I see you dressed for the occasion. You've got your official Hubble shirt on, so that's a good thing. This too. And with that, Mike, I'm going to mute myself now and want to give you a warm skyscraper welcome. Thank you for agreeing to come and speak to us tonight.
Okay, well, hopefully you guys can hear me now. Thank you, Steve. A very nice introduction. So let me go ahead, and we tried this before, and let me see if I can share the screen. Should be this one. Let's see if that works. Yeah, there we go. So now hopefully you guys can hear me. As Steve said, I work in the Hubble Space Telescope operations. I've been there for about 29 years. I went to Hubble just before the first servicing mission in '93. And so I wasn't there for launch, and I wasn't there beforehand, but I am sort of considered one of the old guys of the thing. There aren't too many of us left who have been on Hubble for so long. And that's sort of one of the things I'm going to be talking about. And Steve, you set it up great, because I think I actually hit every single thing you said you're going to be interested in. so at least I'll be talking about what you think I was going to be talking about. And we'll try to see if we can get the chat things. If there's something coming up, if you guys see a question in the chat, let me know, because I may or may not see it. Oh, let me get to this. Okay. So now when people think of the Hubble Space Telescope, what immediately comes to mind are the incredible pictures that Hubble has taken over the last 30 years. I mean, you could spend hours and hours and hours going through just a small fraction of those images. And each one contains incredible science, incredible discoveries that were made of them. And when people think of the Hubble Space Telescope, this is what they think of: the beautiful and amazing pictures. I mean, these were just a few of my sort of favorites over the years. And then this is really what has made Hubble such an iconic legend in the astronomical community. It's the pictures. But I mean, Hubble's been up in space for 30 years. I know there are some people listening to this. Well, I imagine there are some people listening to this talk who actually have never known a time in their lives when Hubble hasn't been in space doing pictures. We have people working on Hubble. We have engineers working on Hubble who were not born when it was launched. It's just an incredible thing. It has really become sort of part of society. I mean, not only do you see the pictures as Hubble pictures are on everything. I mean, they've become, they're not just in scientific journals and magazines and school books like you would think, but people wear them, people walk in them, people drink them. And there's a whole generation of people living, anyone less than 30 years old, and certainly my daughter is one of them, that they've never known a time that Hubble has not been up in the sky taking those pictures. And like I said, it's really quite a phenomenon. In fact, some people actually have Hubble tattoos on their body. Now, the really strange part about this is that I obviously know a lot of people who work on Hubble. I mean, I literally know hundreds and hundreds of people who work on Hubble, and yet I do not know anyone who has a Hubble tattoo. However, I think there's actually someone out there tonight, and I know she's listening, that may be able to rectify that situation. So Alex, if you're looking for your next tattoo idea, keep Hubble in mind. But your parents, who I know are also listening, and I see Maria laughing there, they may not think that that's such a good idea, but it'd be really great for me to say I actually know someone who has a Hubble tattoo through it. So, so obviously Hubble, the Hubble pictures have shown up in magazines, National Geographic, of course, Sky and Telescope. I mean, Hubble is just all over. However, like I said, Hubble's wormed its way into our society at a level that's sort of unprecedented. Hubble Space Telescope actually made the Dive Pacific magazine issue. And it has, and mainly because it was done here because of what's known as the neutral buoyancy tank. And they were training for one of the Hubble missions. This is actually kind of interesting. I mean, I've been lucky enough I can actually have worked on all 5 of the servicing missions 1 through 4, because NASA counts weird. And then, so we've actually worked with training here. This is actually, it's a big swimming pool. The neutral buoyancy lab is actually a huge swimming pool. That is actually a full-scale mock-up of the business end of Hubble. It's sort of the back end where all the instruments and equipment are that the astronauts are working on. And we would actually be training for the missions. We'd be having full-scale simulations with the astronauts working, and they'd be working on here. There's a robot arm. There's a whole shuttle. That bottom part is the shuttle bay. I mean, it's a big pool. And then we'd actually be having simulations. And what was really funny, because all of a sudden you would hear the astronauts talking, and they were talking about loosening this up or putting the certain torque on that nut. And then all of a sudden you would hear them say something about an angel. And it's actually because all these support divers that you see sort of floating around, and this is why the Dive magazine did it, they were actually called angels because they helped keep the hoses out of the way. I mean, when you're in the pool, you actually have a lot of these hoses attached up, and sometimes the hoses would get hung up. And so you'd hear an astronaut call for an angel through there. So it's just an amazing time. But now, Hubble is about the science. In fact, I noticed someone had asked in the chat there, in fact, I think it was Glenn, how long is NASA going to be funding Hubble? And it's pretty much, NASA has said that they'll keep funding Hubble as long as it continues to produce the science. And Hubble is producing science at an amazing rate. This is a graph showing refereed publications. So this doesn't count all the cool articles that you guys read, in Sky and Telescope and National Geographic and Science Magazine and stuff. This is the stuff that is the Astrophysical Journal, the Astronomical Journal, the all the technical scientific papers. And you can sort of see how this graph, I mean, this goes up to 2020, and there are over 1,000 papers being published a year on Hubble. That's 3 papers a day, new papers, and these are refereed ones. These are ones where guys are spending months writing these papers, and yet there's so many people out there doing it. There's over 1,000 being produced every year. This is really a phenomenon, and Hubble has exceeded all the expectations in terms of the scientific return from the mission. One of the interesting things to notice about this graph, and you could stay here and talk along a lot, but I'm not going to. It's this purple amount. That's actually the Hubble archive data. Hubble has been establishing an archive. Every single observation Hubble's ever made is available. You guys can download it. There is a 6-month sort of period where the guy who, the astronomer who proposed the observation gets to have his data for 6 months, but then it becomes public knowledge. And that public archive is a gold mine, and people are starting to mine that. You see almost half these publications are from the archive alone. And that's, Hubble, even when it stops working, Hubble science will continue on for decades past that. And so this is sort of about what Hubble's really about. But tonight, I wasn't going to be talking about the pictures or talking about the science, but what I wanted to do is actually take you behind the curtain, so to speak, and show you what it's like to operate the Hubble Space Telescope and to keep it working day and night, day after day, and to keep all the pictures and all that science coming down in there. Who are the people behind the curtain? What is it that we do day to day to keep the telescope running? As Steve mentioned, I've been working on the Hubble Space Telescope, for over 28 years, almost 29 years now. My friends and I have supported, the 5 shuttle servicing missions. We helped train the astronauts. We've written software for the telescope to create special operating modes that allow the telescope to do things that no one ever thought it was going to be possible for the telescope to do. And so what I actually want to talk to you guys tonight about is what it's like to operate a telescope like that. I mean, it's a telescope that's been called a national treasure. And it's been called one of the most famous telescopes in history, and it's certainly something you think about. because boy, if you mess up on Hubble, you sort of end up in front of Congress, and that's not something you want to do. And so we sort of have to take, a lot of considerations into what we do. We can't just willy-nilly be sending commands up into Hubble. Yeah. So this is the Hubble Space Telescope as it looks today. In fact, this is actually one of the last pictures taken of Hubble back at the end of the last servicing mission 4 in 2009. For those of you who are real Hubble aficionados, you can tell it's a recent picture because of a few items. And can you guys oh, you can see my pointer. So the solar arrays, these are actually solid solar arrays. These are solar array panels. They fold up like a book things. They're really short compared to our old solar arrays. Our old solar arrays used to be about the same length as the telescope. These are our new solar arrays. So, it's at least relatively new, although we've had these for quite a while. We've had these for, almost 20 years, I think. So that's one of the things that sort of clues you in. The other thing is that there's something stuck on the back end of the telescope here. I'm actually going to talk about that a little bit later, but that's not original equipment. That's actually something we stuck on at the last servicing mission, and we sort of left it on there. The other thing, there is a story behind this, but I mean, we may get into it at some point. There's this little white cover here sitting. This is one of our low gain antennas, and this is actually the cover for it. The covers are used during the servicing missions to protect it because they're fairly fragile devices. This is the other one up at the front of the telescope, by the way. They're very, very low tech. There's just low gain antennas. I'm sure half you guys there know more about that than I do. We actually put the covers on when we're servicing it, and this cover was left intentionally. We knew it was on there. It wasn't like, wait a minute, someone forgot to take the cover off. We actually did, and there was a reason we did that. Like I said, maybe I'll tell the story for you, but it makes no difference. The low gain antenna goes right through that cover, so it actually sort of makes no difference. So that's what Hubble's looking like today. So what is it that makes Hubble so special? What makes it so unique? It's not a particularly large telescope. I mean, there are a lot more, much larger telescopes on the ground, huge telescopes on the ground. Being in space means there's no atmospheric distortion. So Hubble certainly has, the exceptionally sharp and high resolution imaging capabilities. But I mean, with the advances in adaptive optics on the ground, there are many telescopes on the ground that can actually get higher resolution and more detailed pictures than Hubble. Now, Hubble typically can do that over a larger field of view than most of the ground-based telescopes. Hubble's entire field of view is high resolution. It's adaptive optics, quality. It's the limit, the best you could get with that size mirror. So that's kind of nice. Hubble also doesn't have to worry about weather, except in some extreme cases, and I'll actually mention that a little bit later. But it's never cloudy in space. We can observe 24 hours a day, 365 days a year. So it never stops performing science observations. That's one of the things that keeps those science driving so long, all those papers. But the real unique feature about Hubble, and the thing that actually none of the observatories on the ground can do, and even James Webb Space Telescope will not be able to do that, is up here. Oh, let me go back, he says. Click my button. It's up here. It's the UV. It's the ultraviolet range. I mean, Hubble can actually get deep into or far into the ultraviolet, and no one else can do that on the ground. It won't penetrate. I mean, this is a good thing. You don't want the UV penetrating the Earth's atmosphere, but there's a lot of very, very interesting science. There's very neat stuff that can only be done in the ultraviolet, which is sort of why and we hear this, people ask all the time, oh, so is the James Webb the replacement for Hubble? No, James Webb is working down here. He's down here. Yeah, James Webb replaces NICMOS, which actually is dead anyway. That instrument does not work in Hubble anymore because it ran out of the coolant for the infrared detectors. James Webb's working down here, way down here. Also, Hubble works here. The best situation you can have is if Hubble and Webb are up there at the same time. And people are actually talking about that. They're using great words like synergy of the two Hubble observations. And so it's not like Webb's replacing us because they can't do UV or visible. And we're the only game in town for that. So you could spend hours talking about specific stats and capabilities from an engineering point of view. And I know there are a few of you listening who would like me to do nothing better than to dive into all the intricate details. Yes, I'm talking about you, Brown and Cannon. But there's not enough time for that. And quite frankly, I think a lot of other people will find that boring, as much as I know you'd love it, Jimmy. I see you smiling there. Yeah, sure. Anyway, some of the stats. Like I said, it's not a big mirror, 2.4 meter. Come on, guys. I mean, that's not huge. F24, it's a Ritchie criterion, hyperbolic primary, hyperbolic secondary. It's low Earth orbit. This actually has some interesting side effects. You're only 335, we're only 330 miles up there. We have a 95-minute orbital period. We go around once around the Earth every 95 minutes. We're moving at 17,000 miles per, 4.7 miles per second. It's about 17,000 miles an hour. We are whipping around the Earth. And so, why are we in that low of an orbit? That's the highest the space shuttle could ever go. And we were put up there by the space shuttle, and we had to be serviced by the space shuttle. So that determined our orbit. Would we like to be in a higher orbit? Yeah, probably. But we loved being able to be serviced. So it was a good thing. It weighs, and yes, you can get, there's no weight in space, but there is mass in space, and there's inertial mass. So, it does have mass in space, and it's heavy, it's 24,000 pounds. And it's also, it's kind of hungry in power consumption, 2,800 watt power consumption, which, I mean, like I said, some of you guys, that's going to really ring with you. I'm not an electrical engineer, and one of the other sort of stats I throw out to people is that when we're running the telescope, our just general running, we are pulling about 65 amps off either the solar arrays or the batteries. We pull 65 amps, and you guys, with the wattage, you can figure it out. It's about 30 volts that we're pulling out. So those are some of the stats. This is, a sort of generic breakdown. This is what the Hubble looks like. There's the back end is the science instruments, STIS, GOSTAR, ACS, NICMOS. That's where all the science is done. Sitting in the middle here, there's you can see there's an old picture because we're up to Wide Field Planetary Camera 3. So that's, we keep replacing this one in the servicing missions. Another science instruments, in fact, that's the workhorse imager. But there's also the fine guidance sensors. I'm going to be talking about those. As Steve mentioned, I actually take care of the fine guidance sensors. These are what allowed Hubble to do the pointing. There's a primary mirror going through there, and there's secondary mirror, and then there's a whole bunch of tube sort of sitting off the end. Someone just asked in the chat about the corrective lenses. Yeah, but we pulled those out. Those aren't in there anymore. It actually is kind of funny. I was just watching something on Hubble, and there, even to this day, you see Hubble documentaries, and they so talk about the corrective lenses. We got rid of those because all the instruments are new in the back end here, and all the instruments correct it themselves. They all have the lenses in them. The mirror was ground wrong, old story, old news, but it was ground wrong perfectly. that was the key. It was ground wrong, but it was ground wrong perfectly, so it was easy to correct for the instruments, once you could get new instruments inside there. Before, on the first servicing mission, we had to put in this great thing called CoStar. It had the things popping out, little arms. We actually pulled that out, and we put a new instrument in there. So it doesn't have the contact lenses anymore. Everything's just built. Think of it as laser surgery. We corrected the things in there. The other thing to remember is that the rest of the telescope, there's a bunch off the tied in. Mainly we're trying to keep light out of the telescope and keep everything nice and warm. This thing's really covered with mylar, this whole thermal thing. In fact, what's really weird, this always sort of blows me away, it's about room temperature. The Hubble Space Telescope is about room temperature on the inside. And all the primary optics and stuff like that are kept about 70 degrees. Things just tend to work better there, and it's easy enough for us to do. We actually have some trouble with things getting too hot. For those of you who sort of know spacecraft things, a lot of times it's trying to get rid of heat. That's the hard problem, as opposed to generating it. We're burning 2,800 watts, and so we've got a big heat source sitting in there. Now, one of the big things, the important thing to remember about Hubble is that it's old. It's very old. And a lot of the equipment on Hubble is very old technology. The telescope's been in orbit 30 years. It was built 40 years ago. And actually, a lot of the technology that it's using is sometimes 50 years old. I mean, so this is an old tech telescope. This was actually one of the original tape recorders that we had on Hubble. It truly used tape, as you can see here. This was actually one.
Chewing like a nut.
We actually replaced it. We did put some solid state recorders in Hubble, but we actually still have one of these original tape recorders in Hubble, and we still use it.
Jeez.
And for those of you who remember using tape recorders, you always remember the problem with tape recorders. And boy, I don't know if you guys can see this. See this little loop of tape right there? How many times are you playing your tape recorder and the thing jumped off the capstan?
Yeah.
And that sort of made it. That's actually why we had to replace this one. It sort of jumped the thing. But so, you have to remember Hubble, a lot of these stuff that we are making Hubble work with is old tech. I mean, you have, it's far less powerful. All the computers on Hubble and all the equipment on Hubble is far less powerful than what you carry around in your pocket every day with your phone. I mean, your phone is so much more powerful than Hubble is, both for computer and communications wise. Your phone puts Hubble to shame. And yet we're able to do quite significant things to it. So how do we operate Hubble? How do we talk to it? How often do we talk to it? How are the pictures sent to the ground? These are the pictures, Steve. These were the questions Steve wanted to answer, me to answer. If you're ever visiting, if you happen to be down in the Goddard Space Flight Center, which is where we run Hubble out of, and you happen to get a Hubble visit, a Hubble tour, a lot of times I may be the one giving that tour to you. And if you ever see this many people in the room, one of two things is happening. Either we're running a test and we actually aren't hooked up to the telescope, we're actually hooked up to simulation computers. We test everything on the ground multiple times before we send it up. Like I said, you don't want to make a mistake on Hubble because you could end up in front of Congress. And so most of the time, if you ever see this many people in this room, it's because we're running a test or something has gone wrong on the telescope. There are times when we do have to go in there and we actually do have to man these rooms. And I think this may have actually been, I think this was a test. Kind of hard to tell. Usually, even when something goes wrong, we don't tend to get this many people sitting in there. There's actually a small core of us who, there's like 5 or 6 of us who end up having to go in at 2 o'clock in the morning. So, we used to have flight operations team. We used to have people 24/7, 365 days a year, having to watch the telescope and having to send up commands and send up loads and dump data. But we actually have an automated computer command system now that actually does most of the commanding and talking to the telescope. I mean, we've been on orbit so long, we've been able to change our ground system a couple times. We've been able to upgrade it, which is phenomenal in the spacecraft industry, to not only, to change the way you operate the telescope. We've actually gone to an automated system, which has made handling, the last year in terms of the COVID pandemic, very, very easy for us because we were pretty much already in automated operations. We do have real people that have to sit down at the consoles about once a week to perform real-time commanding. They've been doing that over the past year. They get sent in. There's only 2 of them, and they get to be 12 feet apart, 6 feet apart. They go in. Actually, lately, we've been only sending one in, and the other one sort of joins up remotely. And so typically, we only have people on console physically sending up commands, typing in commands and hitting enter and seeing the telescope respond. We only do that about once a week. But, that's only if something, if it's all working. If something doesn't work the way it's supposed to be, then you will find us in there. There's going to be a few of us in there who have to go in at 2 a.m. in the morning to try to get Hubble back on track on performing the science. Luckily, this past year we've been able to do it. I don't actually have to physically go down there. I can actually do all my stuff remotely. We do have to send someone in there every once in a while, and so I've been responsible for sending guys in. Actually, quite a bit the last few months. We've been dealing with some gyro issues in that. So how does Hubble talk? How do we talk to Hubble? How does Hubble talk to us? This is the Hubble data pipeline. It sort of uses a roundabout path to get to us. We make use of what's known as the TDRS satellites, the Tracking Data and Relay Satellites, TDRS. That's why we call them TDRS. And then, so Hubble can actually talk to the TDRS satellites, these smallish, but large, these antennas on the side, they're about 2 feet across. These are high gain antennas. They actually communicate to the TDRS satellite when they can see the TDRS satellite. We'll talk about that in a second. The TDRS satellites talk to the ground. They talk to ground stations at White Sands, New Mexico, out there in the White Sands Missile Base. In fact, now this is actually the only way Hubble can ever be affected by weather. If there happens to be really, really intense thunder and lightning storms at White Sands, we can sometimes lose communication with the telescope. It doesn't happen very often, obviously, because they're getting pretty good at being robust. But every once in a while, they have a storm come in that's so intense they'll actually tell us they can't give us the contact that, you know, we were supposed to be getting. It happens maybe once every few years, but there's no thing. So Hubble actually can get affected by weather every once in a while. Although it doesn't care. We don't have to communicate. It's not like we lose science that way, because even if we were supposed to be dumping data, we can dump it at another time. So it doesn't affect the science. So White Sands sends it to us at Goddard in Greenbelt, Maryland, Goddard Space Flight Center. We actually strip out all the engineering telemetry. That's what we're interested in terms of the trying to run the telescope and be able to do that. And then we actually send the pictures, the pretty pictures get sent up to the Space Telescope Science Institute. They're the ones who actually put out the pretty pictures. People always ask me, oh, do you guys get to see the pretty pictures? No, we have to wait until the Science Institute makes them pretty and shows them back to us. So it's actually kind of nice every once in a while, the guys from the Science Institute will come down and tell us, you know, oh, here's the nice pictures of the stuff that you guys were taking it. Now, when we want to send commands up to the telescope, we actually have to use the same path. It is actually a relatively long path. We actually do have to take the speed of light into consideration when we're commanding the telescope because of the distance involved. There's also another problem in that the teeter satellites are geostationary satellites, so they can always talk to the ground stations. But that means they are stationary, they are very high orbits, we are low orbits, we are zipping around the Earth. We cannot always see one of these guys. We can only see these so often. So we have to be really good at scheduling when we know we're going to be able to see the teeter satellites. We have to schedule it with them. We have to more or less sign up, tell them we want to use your satellite. We need it for so long. You know, we're going to be using such and such a band, and that. That's sort of why the Hubble has onboard tape recorders or solid state recorders, data recorders, so that we can send the data back down on the ground later. You know, but it also means we can't sit on the ground and send commands for the telescope to take pictures. The telescope needs to know what it can do. So when we can't talk to it, we actually send up command loads to the telescope that contain commands that has it execute for about the next 24 hours. Each command load has about 24 hours of commanding. Pretty much every single second is in this command load. Think of it as a huge computer program. Essentially that gets loaded up in the computer and the computer starts executing it, and every single second, you know, it knows what it should be doing. So we put that up for about 24 hours of time. And so we have to send those loads up. Now it's our automated system that's actually sending those up these days. It used to be our flight ops team, but now it's actually done automated. So, you know, that's sort of how we can get data up and back and down to Hubble. Now, that sort of it sort of brings up an interesting point that people don't realize. You know, we are in this low Earth orbit, and the reason is because that was the highest the space shuttle could go. So the Earth is actually kind of big from where we're at, and you know, we're going around it every 95 minutes. So it actually means the Earth gets in the way. The Earth gets in between because we're going around the Earth. The Earth will go in between us and what we're looking at about half the time. So we'll be looking at something, and then we have to stop because the Earth literally gets in the way. And so we have to stop looking at that, and then we have to wait till the Earth gets out of the way, and then we got to go back to continue taking, you know, data on that object, because the most we can typically get is about 40 minutes before the Earth gets in the way. So we do that over and over and over again. We have to acquire it and then stop and reacquire it and stop and reacquire it and stop. Now it's not like we have to close the cap at the end, the lens cap. We actually don't. We do have to shut down the instruments. We have to turn off the high voltages and stuff like that because the Earth is bright, especially when it's cloudy. And so we actually do have to do that, but the telescope will be pointing at the Earth. We can't see anything. Everyone always is thinking, you know, Hubble's being used serendipitously as a spy satellite. The Earth is too close for us to focus, so we can't focus on the ground. It's too close. Hubble can't get that focus. And we don't have any instruments that could actually do it anyway, because nothing can take that kind of light. So the Earth gets in the way. Now, if some of you are used to playing with orbital dynamics, you should be able to say, wait a minute. Shouldn't there be two spots in the sky that the Earth actually never, gets in the way? Wouldn't that be the orbital poles of the FHST orbit? And sure enough, you guys can give yourself a gold star. There are actually two places in the sky that the Earth won't get in the way. We call these continuous viewing zones, CVZs. And if we're pointed at something there, we can just keep on looking forever. Now, The CVZs change a little bit because our orbit precesses, goes around. If you've ever seen the orbit tracks, and there are plenty of programs on the web, and you've probably got them on your computers to do the orbit tracks. So the CVZ moves a little bit, but there are actually regions of the sky that we can actually observe without having to worry about interruptions, except there is this thing called the South Atlantic Anomaly, which I'm not going to talk about, Carrie, sorry. But it actually makes us shut down even if you're in the CVZ sometimes. So there's all this thing. So the telescope has to be, starting and stopping and continuing. So we have to be really good about taking things into considerations and figuring out the most efficient ways to schedule the telescope. We actually make use of a very, very rudimentary AI system, mainly because it was developed, 30 years ago, to do this. This is actually what's known as a MEG, which stands for the Emission Events Graphics Generator page. We call it the MEG timeline. There's actually a lot of information on here telling you what's going on. This is for day 317 in, 2014. This is an old MEG, 6-year-old MEG. This is what the telescope was doing 6 years ago. There's a lot of information, allows us to see what the telescope's doing and what we're doing. There's things about day, night. The telescope, as it's going around the Earth, sometimes the sun is out for us. We're in daytime. And the solar rays can be charging. When we go into nighttime, we can't obviously use the solar rays. We have to go to the batteries. And so we start pulling from batteries. This first line up here, the day-night, that shows it's day-night. Here's the only thing I'll mention about the SAA, Carrie, is that the SAA does get in the way. And this tells us the levels of SAA. The SAA is what's known as the South Atlantic Anomaly. It's an area of high energy particles that will sometimes cause the electronics to have bit flips. And so we can't operate inside of there. So we actually have to shut down for a bit, while we're doing that. There's more things about what the FGS are doing, the fixed head star trackers, there's occultations. This is the Earth getting in the way. We can't observe here because the Earth is between us and what we want to look at during this time. So the telescope can't do anything in here if on the Earth. It actually can do things like take flat fields and do all sorts of calibration stuff, and a lot of that's scheduled in these downtimes, if you will, where it's doing Earth. And there's also things for the instruments, telling you what instrument's doing that. This was a wide field camera 3 observation. There were observations being taken. Then we get into science data recorders, which recorder recording what. Here's the TDRS, telling us what TDRS we can see. There's one called TDRS West. Here's where we can't see it. ZOE is zone of exclusion, so we can't use it. Here we're recording on the tape recorders there. So there's all sorts of information. This has to be really scheduled up. As to what's going on. We produce this about a week at a time. We schedule the telescope, even though, like I said, we can only load up about 1 day at a time, 24 hours at a shot. That we actually generate this scheduling for a week at a shot. So we know what the telescope's doing for a week at a time. So how do we move the telescope around? How do we get it to point? And make it stay accurately pointed at the different objects in the sky. There's a bunch of different instruments, combination of instruments and stuff that allow us to do that. There are reaction wheels sitting up here. This is sort of where they are in the telescope. There's 4 reaction wheels for that. There's fixed head star trackers that look out the side. Yeah, you see them here, and I got a better picture of them later. And then there's gyroscopes, of course. There's always our infamous gyros. And then there's the fine guidance sensors through here. And it's sort of a combination. We use the combination of these things to point the telescope. The first thing, and everyone asks this question, does Hubble have thrusters? Doesn't Hubble use thrusters to move it around? We all see it in the movies. That's how you move something around in space. You use thrusters. Hubble has no thrusters at all. There is no thrusters. There is no fuel. The way we actually make the telescope move is actually we do something we have called reaction wheel assemblies. And this is, I stole slides of, during this talk, you'll see all of a sudden it'll look like a professional slide pop up here. I stole these out of talks that the various engineers have given over the years talking about it because they had good pictures. Hubble's makes use of the reaction wheels. The way these work, it's a conservation of angular momentum bit. Essentially, they're big, heavy wheels. Once again, they have inertial mass. On the ground, they weigh 105 pounds. They're big, heavy, although in space they don't weigh anything, but they do have the mass. You spin these up. You start spinning that wheel up in one direction, the telescope's actually going to start rotating in the opposite direction. And so if you have these oriented in the right directions, stuff like that, you can actually make the telescope move in any way you want by spinning these things up and spinning them down, spinning them clockwise and then spinning them counterclockwise, you can do this. And this is how the telescopes actually moved. And so technically you need 3 of them. I mean, if you think about it, you say, well, I've got 3 axes. I mean, I'm floating out in space. I've got to be able to move the telescope in 3 axes. So you think I must need 3 reaction wheels to be able to get the motion around 3 axes. Hubble has 4 of them. We use 3 of them at any one time. And so actually, we actually use all 4 because we balance them out a little bit better like that. You need 3 of them. So we could actually have one of them have a failure and do that. And we've actually figured out a way we could actually still do science even if we had 2 of them working. It's because of the way they were set up. There's enough cross-talking along the axes that we could actually do it. We actually have it. So this is an interesting way to move the telescope. These are only 105 pounds, the equivalent mass, inertial mass for that. The telescope is 25,000 pounds. So I don't, you start spinning up a 100-pound wheel, the telescope's not going to move very fast, and it doesn't move very fast. In fact, Hubble moves about as fast as the minute hand on a clock. For those of us who remember analog clocks and remember having these sitting here, so that's how fast Hubble moves. So it actually takes us a half an hour to turn the telescope completely around and point it in the opposite direction. So reaction wheels are cool because they never run out of fuel. They're powered. They're DC brushless motors. So all we got to do is power, and we've got lots of power. But they don't make you move very fast. And so we have to, this is one of the other reasons that we have to be really efficient with our scheduling, because you want to be able to schedule observations that are relatively close together to each other. You want to be able to look at things that are near each other so you don't have to do these big slews. Otherwise, it's going to take you forever just go from point A to point B. I mean, a lot of times we'll spend, there's a half an hour. It's like, go get yourself some coffee and a sandwich while you're waiting for the telescope to get to the next spot. And so that's something you sort of have to keep in mind while reaction wheels. The other big thing Hubble has are the rate gyro assemblies. These are the infamous gyros. These are the Hubble gyros, which have sort of been giving us problems throughout the years. These are the main workhorses of the Hubble point and control system. They're actually mechanical gyros. Believe it or not, they're actually, they're physically spinning, they're very spinning gyroscopes. This is one that's sort of been taken apart. Once again, this is taken from another thing. I'm not going to go through it. Some of you engineering nerds will love to read the details here. They spin relatively fast, 24,000 RPM. When they're spinning, they're actually floating on a gas bearing. If they ever stop, if they ever stop, you actually bring them down, they'll actually settle onto the thing. So you actually don't want to stop these things from spinning, because that's when you sort of ground on the bottom. And to get it to lift up off, you got to start spinning up again. So starting and stopping these things are the scariest things, but they'll keep spinning for the longest time. But they have a problem, and in being mechanical, there's these things called flex leads. They're very, very thin wires. You can see that wire sitting next to that dime. These are very small wires. These carry the entire current for that gyroscope. It's a balanced torque loop control system. So it actually does have milliamps flowing through that little wire. And those flex wires have actually what's been giving us trouble. Hubble has 6 gyros on board. Currently, only 3 of them are still working, and one of them is being a real pain in the butt. But we do have 3 of them working. And once again, we have to control the telescope in 3 dimensions in space. And so you'd say you have to have at least 3 gyros to do that. And everyone pretty much thought, yeah, Hubble would not be able to operate on less than 3 gyros. That's why they gave us 6. They just didn't realize the gyros were going to start having these problems like this. But actually, we've come up with some very unique ways of making use of other instruments on board Hubble, so we can actually keep on performing science even if we only have 1 gyro left. That's sort of why people think we can actually be able to operate Hubble, we've got a lot more years left of us. We have 3 working gyros. We only need 1. And so we think we can go well into the late 2020s and even beyond. So yeah, knock on all sorts of wood. Now, the gyros are actually used to help keep track of where Hubble is pointing. The gyros are incredibly precise instruments, but they work best at keeping track of where you are when you're moving small amounts. That's where they shine. They're they're the best you can get in terms of measuring small motions. The trouble is, if you move a lot, like you're slewing from one target to another target, the gyros will get a little bit off. It has to do with the electronic biases that are on the gyros and stuff. But if you just use your gyros to keep track of where you are, they're rate gyros, they're measuring rate around an axis. When you slew from one target to from one observation to another one, you can actually be off by hundreds of arc seconds, which is not good. That's actually being off a lot. And so the gyros, while these are what control us when we're doing, our small maneuver and stuff like that, they don't work that well in keeping track of where we are for the other stuff. For that, we have to make use of another piece of instruments on the Hubble known as the fixed head star trackers. This is a picture of the Hubble in the shuttle servicing bay during one of the servicing missions, being either lowered or lifted. I don't know which one. I think I was being lifted out on servicing mission 4. These black things here, the things people call the eyes of Hubble, there's 3 of them. These are actually what's known as fixed head star trackers. They actually are looking at different angles, which is why these are sort of elongated because it's pointed way down. And you can see that one's pointed down at this angle, that one's pointed at this angle, and this one's actually looking straight out. So they actually look at different parts of the sky. And what I don't expect you to read or understand much of this, mainly just to tell me what to talk about here. The fixed head trackers are actually wonderful old tech analog devices. I mean, you guys who like old electronics, I mean, you can't. This is the workhorse of the space industry. It used to be. Now they're all digital. But these analog fixed head star trackers, they had image dissector tubes. I mean, incredible photo multipliers. I mean, they're just fantastic old tech. So what they do is they look out into the sky. I mean, they have field of views of about 5 degrees on the side. They have very large field of views. In fact, the full field of view is like 10. We are using a reduced field of view of around 5 degrees on a side. And what they do is they can see stars down to about 6th magnitude. And so this is actually a picture of a tool that we use to watch these fixed head star trackers when they're working. The way the fixed head star trackers work is, like I said, it's a scanning technique. It scans back and forth and up and down, back and forth, like the old TV raster scans. It's scanning back and forth. It's looking at the beam and seeing if it detects any light. And so we actually see on this tool, we actually see it scan to the left and go back to the right, and then it goes up and scan to the left, go back to the right. If it sees anything, it pops over. And so what it does, it can detect certain stars. This tool knows, it's got an internal star chart to it, so it knows that when the telescope was pointed where it should have been pointed, there should have been stars at all these positions. The circles, triangles are variable stars, lots of variables out there. And so the circles, normal stars, the size is about the right magnitudes. The FHST can't see all these are just too faint for the FHST to see. But what it does is it goes through and it figures out, oh, I see a star here. Well, actually there's 2 stars right next to each there, so that one's gonna be a little problem to use. And it sees another star here, and it saw another star here, and it saw one here, saw one here, saw one here. And so it goes through and says, hey, I see 5 stars here. And it tells the onboard computer where it sees it in terms of an X and Y internal to the instrument itself. The instrument has no idea where the telescope's pointing. It just says, hey, I see a star, 4 units up and 3 units to the left. So it tells that to the computer. We always use 2 FHSTs at once. They're pointing in different parts of the sky. We know sort of where they're pointing. The gyros have kept track of us well enough so that we know roughly where the telescope is pointing. We have a rough idea of where it is. So we know what stars should be around. The FHSTs come in and they tell us, hey, I found these stars here. And then they actually use a very interesting piece of software. It's a pattern matching algorithm that was actually developed specifically for these fixed head star trackers to be used for the Space Telescope. And it matches patterns of stars. And it says, if the telescope's pointed in this direction, this FHST should be seeing this pattern, and that FHST should be seeing that pattern. And if they're a little bit different, it can actually figure out where you're pointed by this pattern matching. I mean, it's actually very good about that. It can get us, it will then say, oh, the FHSTs see you pointing here, I gotta move you a little bit. And we can actually now point the telescope to within about 10 arc seconds of where we wanna be, which is really good. I mean, that's, we're getting down 10 arc seconds. Most of us using telescopes at home, say 10 arc seconds is great, that you're close enough. Well, it's not close enough for Hubble yet. The FHSTs get you to within about 10 arc seconds in there. Now, I just have to take, so there was this infamous pattern matching program. There's been a lot of technology spinoffs from Hubble. And you could, like I said, you could talk a long time. There have been whole talks about talking about the technology spinoffs. One of the more interesting ones is, because I use these FHSTs a lot, had to do with scientists that were studying whale sharks. They had a problem of they couldn't keep identifying which whale shark was what. You know, they try to tag them. This one's obviously got a tag on it. You can see it floating up behind it. But they wanted an easier way to sort of keep track of whale sharks. Someone actually realized that, wow, doesn't the pattern on the whale shark sort of look like a star field? And sure enough, someone said, you know, those HST guys can identify star fields really well by pattern matching. And so they actually took our software that we use for the fixed-head star tracker pattern matching, and they use it now to identify whale sharks. And so they can keep track of them. So like I said, it was just a fun little aside for that. So you can get the FHSTs, get you down within about 10 arc seconds. Not good enough though to get the science instruments fired up yet. We've got to use what's known as defined guidance sensors. And this is actually what I take care of. This is a picture of what the Hubble field of view looks like. You can imagine if you actually could look through the Hubble telescope and think of like using an illuminated reticle eyepiece or something like that. The Hubble, this is, you know, the entire telescope can see this big chunk of sky. And what happens is the instruments are looking mainly down the middle. Some of them are off to the side a little bit. It's because everybody wants to be in the middle because that's where your best optics are. That's where you get your best imaging. So that's where the wide field and camera 3 instrument is. And so there's that. On the edges, there's what's known as the fine guidance sensor around them. And these are huge, this whole area that says FGS3 and FGS2R2 and FGS1R, because we've replaced fine guidance sensors over the years, so we got to call them something else. The other instruments sort of stay where they are and just look through the thing. The FGS is actually, FGS1 can look anywhere in here. It can actually move around anywhere within this shape, and FGS2 can move anywhere within this shape. For obvious reasons, these field of views have started becoming called pickles. They're known as the FGS pickles because they have a pickle shape, and they are referred to it. In fact, we have a tool called the FGS pickle tool that allows us to watch the FGS's pickles in motion. But it's very interesting. The FGS can actually move around in here, and that's what actually helps us get down into them. I do not expect you, maybe even be able to see much of this, let alone understand any of it. And the FGSs are amazing instruments on their own. I mean, yes, they're guiders for the Hubble Space Telescope, but they're probably actually some of the most intricate instruments ever built for Hubble, where do you find guidance sensors? And that's probably still true now. You know, these things are works of art. They're white light shearing interferometers, if that means anything to anybody. Probably doesn't mean a lot. They use mirrors and optics to take a light from an incoming star. You know, here's the telescope down at the bottom. Light comes from the star, come off the pick-off mirror. They take that light, they break it into 4 different pieces, and then they recombine them. And if you guys have some physics background, if you take light, you split it apart, you recombine it, you get what's known as an interference pattern. And this is actually what the FGS sees for a star. It doesn't see an image, it doesn't see a star image, it sees an interference pattern, it sees an intensity signal that it gets through. This is sort of like this is an axis, this is an x-axis and y-axis. This is the signal strength coming through here. So the signal's, you know, roughly about 0. All of a sudden the signal peaks up, and then the signal goes really low, and then it goes back to about 0. This is known as an S-curve because it looked like an S to somebody. Interesting thing about S-curve, it has a very steep middle in here. The middle goes through 0. And so what the fine guidance sensors do is they find the middle of these S-curves. There's a whole technique for it to do it. Finds the middle, and it sits there because if the telescope starts to move a little bit, it gets a big signal because this thing is so steep. This curve is so steep in the middle. The FGSs get a very big signal for a very little piece of motion. And so that's why the FGSs can actually guide down to the milliarcsecond level. The FGSs are sensitive to motion down to milliarcseconds. That's 0.001 arc seconds. And the FGS can tell that if the telescope's moved that. That's where Hubble gets its amazing pointing capability. And it's, you know, there's lots of descriptions of, you know, of what this is like. It's like you're standing in New York and you're holding a laser pointer and you're pointing the laser, you know, centered on a dime, but not only on a dime, you're centered in the middle of the president's head on the dime in Washington, D.C. from New York. That's how steady we can hold the Hubble Space Telescope, and it's all because of these FGSs. because they can sit in here and write into it. This is this, say you wanted to take a picture of this galaxy. This is the background image is just an old Palomar Sky Survey image. Say the instruments wanted to take a picture of the galaxy. The way you do it is, notice how there's going to be stars sitting in these FGS pickles. The FGSs can move anywhere in these pickles, and you need to go find guide stars. We need to have 2 of the FGSs lock up onto guide stars. What we do is we send the FGSs out, and we tell this FGS over here is like we say, hey, there's going to be a really nice bright star here. Because remember, the FHSTs are going to get us within 10 arc seconds. So good enough. I mean, the FGS is going to be able to go out, and it's going to be able to say, hey, there's a star here. I'm going to go find that star. And then we tell FGS2, hey, there's a star up here. You go find that star. You guys go lock up on that star. And when you find them, you lock into them. And then we put them into the control law. And then they'll hold the telescope locked in it so the science guys can take pictures of the nice galaxy. Great, works fine. Like I said, the FGS is an amazing instrument. This nice little S-curve here allows you to have a great thing. But it is assuming that the stars are one perfect point sources, and more importantly, there's only one there. What happens if you happen to have 2 stars close together? Now, these stars are close together, believe it or not. This is a ground image. These days, this isn't a very big thing. These are 0.16 arc-second separation of a double star here. This is a ground image with adaptive optics. You can see it, 2 stars, no problem. This is what it looks like to the FGS. The FGS says, heck, I could drive a truck through the middle of here. And the problem is the FGS can't lock onto this one. It needs a single S-curve to be able to lock up onto it. So we can't use double star as a guide star. You can say, well, okay, I mean, 0.16, probably very few atlases in the world will ever tell you if they're double stars down to that level. The FGSs are actually even worse than that in the sense that here's a double that's actually 70 milliarcseconds apart, 0.07 from the ground. From best telescopes on the ground, it only looks like a single image. Although adaptive optics is getting really good these days. These guys could probably split that these days. But certainly back 10 years ago, that wasn't the case. Once again, but the FGS sees it as this. The FGS is still seeing this thing as being like, this is not a star, guys. There are 2 things here. So it actually, there's a little sort of interesting gotcha coming out of here. That we have a guide star catalog. I mean, there's something called the Hubble Space Telescope guide star catalog. You can download it. And it doesn't resolve doubles any closer than 1 arc-second. So actually, a lot of the guide stars that we tell the telescope to use are actually previously unknown double stars. And we discover them because the FGSs fail to acquire them. This is sort of it's sort of a weird thing is that the telescope, I mean, we'll get paged and I'll get notifications that something didn't work, and it didn't work because it was a double. It was a double that no one ever knew about. And so investigating these sort of acquisition anomalies, as we call them, we actually result in discovery about 1 to 2 new double stars every week. And we've been doing that for 30 years. And so I've actually been involved in publishing out catalogs of these doubles. We've actually found new variable stars too. So the FGSs sort of do science on the side, even when we're just trying to guide the telescope. These things are so sensitive, they're actually making scientific discoveries on the side. Now, when they do actually acquire the guide stars, they provide actually, there are 4 PMT tubes in there, old school. Yes, I know, old school PMTs, but very precise, old school. And we do it over long periods of time. The FGSs are actually recording data 40 times a second. So every second we get 40 different measurements of the star's brightness and position. That actually led to another very unique discovery that we serendipitously made with the FGSs. We were looking at data and we saw this. And you can sort of see here, there's the data is the stars, and then there's error bars going through, and you sort of see the, smooth out thing. We were going along, and all of a sudden, this is the brightness seen by an FGS. The stars should not change brightness. All of a sudden, things are going along, and we see the brightness go up and down, and back up and down and up, and then it settles back out. And really fast. This is 0.1 seconds. And so we actually saw that this happened. And we looked, I worked with some astronomers, and we looked for something like this. We actually went into the FGS data because we save all the data. We looked at thousands of different observations over many, many years of Hubble observations, and we found this. And it actually led to a new discovery. that Hubble made. So I was involved in this one. And so we actually discovered the smallest known Kuiper belt object. The idea is that, floating way out in the Kuiper belt, there was this little object. There was a background star. When it goes in front of the star, it creates this pattern, and then it goes off of it. There was a diffraction signature seen in it. The object we discovered was only 3,200 feet across, so 3,000 feet across, hence the word smallest. Up to this point when we saw this, the smallest Kuiper belt object known was 30 miles across. And so we sort of broke that record by a long shot. We went from 30 miles down to 3,200 feet. It's 4.2 billion miles away. It is out there in the Kuiper belt. And you couldn't, of course, see it because it would be about 35th magnitude, but the FGSs could detect it. And so it's just, they're just sort of amazing instruments. Now, I know I'm getting here, and so I'll try to finish up here real quickly here. There are a couple other things you do have to worry about when you're just floating around in space. Some of the things I've had people ask me over the years, does Hubble ever worry about getting hit by a meteor? And we usually say, well, that's a very, very unlikely event. However, we do actually do something about that. And there are certain times of years, you guys obviously know, we're amateur astronomers here, you expect certain meteor showers. Sometimes we expect them to be particularly large, although, darn it, if you're from the ground, they never seem to pan out the way the experts say they do they? But there have actually been meteor showers that, have been known to have these clumps. And we will actually do something in those cases. The idea is that we want Hubble to appear to be a small target to the meteors coming in. And the way we actually do that is we can actually point the telescope in the same direction the meteors are moving, so opposite from the point that they appear to be coming from. And then that way we turn the back end of the telescope to the meteors. What the meteors see is they see this for Hubble, very small target. We make it so the solar rays are flat, and the big high gain antennas are just always stuck out there. They're small targets anyway. They're only 2 feet across. But this is the back end of the telescope. And so, we've actually done this in the past. There have actually been a few meteor showers that they've been predicting such large peaks that we've actually done this. And what we actually do is we just find a target that's in the right part of the sky. So many people want to use Hubble and they want to look all over the sky. It's relatively easy for us to say, we need to point the telescope over here. Which scientists wanted to look over there, and there'll have been someone who would have submitted a proposal, to look at something very near there. And so we can actually just go through our observations and find a place to be able to point to it. Then the answering question is, have you ever been hit? Yeah. If you guys look here, this is our high gain antenna. There's a hole in it. We actually got punched through a piece of something, space debris or small meteor, actually punched a hole through one of our high gain antennas. I guess that's trouble having them still hang out there. This actually happened relatively early in the mission. We didn't notice it until the servicing mission when they actually had the shuttle grabbed us and they were doing a photographic inspection. The guys looking at the photographs said, wait a minute, there's a hole in the high gain antenna. So we actually never even knew it had happened at the time. Yeah, we've been hit, and we know that's actually the solar rays. And if you think about it, the solar rays are really hanging out on Hubble. They prevent, we have them pointed 90 degrees to the sun, so they're flat onto the sun, getting as much energy as they can. They actually get hit a lot also. We know that because when we've been in the shuttle, they've taken pictures, and I meant to find a picture of this, but I wasn't able to do it. We see the solar rays have sort of like a glass front to them. It's special material, but it'll be like fractured. Sometimes, though, the meteorites will actually go completely through the solar array cell. It'll actually short it out. We actually have shorts from the solar array every once in a while. What it does, it creates an electrical path from the solar array right to the structure of the telescope. So we actually get stuff, what we call as structure current. We actually have a few amps running through the telescope structure just because the solar rays are shorted out to it, because pieces of meteorites have pierced the things. So we are worried about that. Meteors, though, don't worry us pretty much as much as space junk do. We're actually getting more worried about getting hit by a piece of space junk. This is getting worse and worse as time goes on. Everyone's launching everything into space, and they don't tend to think anything about throwing things overboard or leaving their rockets there or exploding things up, or even having some countries explode things up on, potentially to create a bunch of space junk. We actually have contingencies planned for this to happen. It turns out the military is actually tracking most of that space junk. They can see things down to about the size of golf balls and probably even lower. Some of you I know could probably tell me about that, but can't. You have to kill me. But the military actually will tell us. They have a great way. They call it a conjunction event. We'll get these emails saying that there is a possible conjunction event for HST. Now, conjunctions are very neat to see in the sky. We all just saw one recently, right, between Jupiter and Saturn. But conjunction events when you're operating a spacecraft is not something you want to happen, because the conjunction event means that your spacecraft and another piece of junk are going to be at the same place at the same time. And that's not a good thing to have happen. And so we actually do have something. We typically will do what we try to do for meteor showers. We have a routine where we point the telescope in the right direction and put the solar rays sideways so that they present it, and we can do that. But you don't know if you're going to be able to communicate with the spacecraft to be able to do that. The things for meteor showers is exactly when they're happening months ahead of time. You can plan for it, and so we just put that into the observation. These conjunction events, will be like, hey, this is your 48-hour warning or your 24-hour warning. You've got something coming up on you. So we've actually developed a routine. It's called the orbital debris avoidance macro. It's sitting in the spacecraft computer, and we can actually use it. We can load it up beforehand with certain information. And this was actually, our flight software people do have good sense of humor, because if we ever had to use this, it would sort of be what the acronym it's the oh damn moment, because something's coming in and we need to avoid it. Now, luckily, we've never so far had to use it. Knock on all sorts of wood. We've had some close calls. We've actually been to the point of almost tripping this off, almost letting this ODAM macro run, but it hasn't. They waved us off at the last minute. They said, no, it's going to miss you by so many hundreds of meters and stuff. They're that good. But that's really sort of the things we have to worry about these days. So that's sort of a brief look into how we operate the Hubble Space Telescope. Now, if you remember, I showed you this picture before, and I talked about, this is a recent picture, and I said I could tell because of this thing sitting on the back end of the telescope. This is actually what's known as the soft capture mechanism. This is something we put onto the telescope at the end of the last servicing mission. We're going to be operating Hubble for as long as we can, continue to perform the science observations. As long as Hubble's doing science, I don't think anyone's going to say turn it off. It's just it's too cost effective at this point. They've got so much bang for their buck that they can't shut it down. As long as we're doing the science, as long as we can keep it pointed and do that, we'll be doing it. So hopefully we'll be into the late 2020s, hopefully beyond. Hopefully I'll be able to retire on Hubble, maybe even go longer. But eventually Hubble's going to stop working. Something will wear out in that. When that happens, there's actually going to still be one more mission to Hubble. Hubble will not be dead even when it stops working. They aren't going to repair it. At least that's not the plan, as much as many people would like to do that. But rather, they have to help dispose of it. Remember I talked about all the thermal shielding and stuff like that, and I said we could keep the mirror at room temperature. Well, there's a lot of stuff around that mirror to protect it, which actually means that if the Hubble starts deorbiting, the mirror will actually hit. Now, most likely it just hit an ocean, but it could actually end up.
Why?
It could end up hitting someone's house, and that would certainly be bad PR. So we actually needed a way we could send up a spacecraft, attach it to Hubble, and either boost it up to a higher orbit, or more likely just drive it down so that we could put it into the ocean, where hopefully we just don't hit one of those whale sharks. So there will be one more final mission to Hubble, but that's just to sort of deorbit it or boost it up. If you're ever wondering what's Hubble looking at, there's this wonderful, wonderful website, spacetelescopelive.org. Easy one to remember, spacetelescopelive.org. It shows you what Hubble's looking at now. Now, obviously, it's not the picture. They use background pictures from either the Sloan, this is the Sloan Deep Sky Survey picture. If they don't have a Sloan picture, they'll use the old Palomar prints or someone, they grab picture. I mean, think of this is, running off Google's type engine. engine. And so this is showing you where the telescope's pointing right at this moment. It'll even tell you what it's doing and who it's doing it for. And you can actually view the research proposal. So spacetelscopealive.org is a wonderful thing to say, what is Hubble doing right at this moment? I mean, I use it every once in a while because sometimes I'm curious as to just what in the world are we looking at now, or what were we supposed to be looking at and we aren't because the dumb fine guidance sensors didn't grab their guide stars. There are some other sources, HubbleSite.org. I mean, just Google it, you'll find these. Hubble is out there everywhere, easy to find, and easy to do all sorts of things. And so that I'll leave that with this picture. This is a real picture of Hubble floating up in space. In fact, people say, how do you know it's a real picture? This little thing right here is a reflection in the space shuttle window of the telescope. And so it's actually a reflection of it. This is taken out the space shuttle window as they left it, as they were flying away from it. So this is probably the last picture that will ever be taken by a person of Hubble, although you never know if some people have their way. So that's what I had to say. Sorry for running over a little bit, but didn't do too bad.
That was great. We do want to have some time for some questions.
Yeah.
You mentioned space debris. Somebody asked about, are you concerned with the new constellation of satellites that like SpaceX is putting up or anything like that?
Those guys too are going up higher than us, and so it's only when they're sort of going through our orbital area that we would be concerned about them. And believe it or not, there was actually one time that they were sort of going through our space when we were sort of going through it, trying to go through it. It turned out it wasn't really close. It didn't get much above. In fact, I think it was, we got like a week out and they said, probably not. And sure enough, it turns out we weren't going to be that close. So we're in kind of low Earth orbit. They're actually going up higher. Somebody put actually up a bunch of what's known as CubeSats up in our same orbit as the same orbital height as us, which was crazy. We're still mad at them, and we have to, every once in a while we have to worry about them coming back around. So it's mainly junk floating around, and so yeah, we are very concerned about it. And like I said, we have these procedures in place that essentially we duck and cover. But we cannot move out of the way. And unfortunately, most of the space junk can't either. It's just junk.
Somebody else asked about roughly how much of each orbit is actually spent observing.
The actual about half of it, about 40 to 45 minutes. It depends. Sometimes it's a little bit longer, 50 minutes. Sometimes it's a little bit less because there's a South Atlantic anomaly. Sometimes the South Atlantic anomaly and the Earth occultation will actually add totally together, and so you actually get whammied twice, and so you can only observe for about 30 minutes. So at least half, a good rule of thumb is that you're observing your science target at least half the time. When you aren't observing your science target, you'll be doing calibration stuff because we can turn on the internal lamps. The shutters are closed of the instruments, but then they turn on the internal calibration lamps. So you can actually do more, and all the observations are all calibrated, obviously. So you're doing things for science. But yeah, unless we use the continuous viewing zones, we're only getting about half the time where we can really be on target, collecting photons from the target, old photons.
Okay. As a suggestion, if people have questions, if you could unmute yourself, ask the question, and then mute yourself again, I think that would be good. We'll have some other questions from people.
Hi, I have one.
Yes.
Hello. First of all, thank you for a wonderful talk. I wanted to comment about the wattage. 2,800 watts doesn't seem like a huge amount of power. I mean, I can run my whole house on that, but I guess if it's running constantly, it's a lot. But I'm looking to go solar, and I'm wondering about those arrays. Do you know how many watts they are, and like what kind of batteries, like what size volt battery do they have?
We're using we use nickel hydrogen batteries.
Okay.
And yeah, to reference sort of the first part of your question, yeah, it's not a lot of wattage. I mean, it was built not to be a lot of wattage. I mean, there aren't a lot. There's a computer. There's computers and there's some solid state recorders. Not stuff taking it. But when you think about I mean, we have, you know, we're only in daylight for about 45 minutes of the orbit. I mean, the other thing about, you know, the fact that we can only observe about half the time is we're only about half the time can we be running off the solar rays. So we're pulling 70 amps off our batteries every 45 minutes, and we do it for 45 minutes at a shot.
Wow.
We are deep cycling our batteries.
Yeah.
Which is, everyone thought this was going to be a problem. We actually have replaced our batteries once. But our power engineer guys have just been phenomenal in learning how to make the batteries last longer. I mean, how many of you guys have laptops that are, what, 3 years old and the batteries don't work anymore, right? Because they won't charge up and they won't hold the charge. Hubble's been running 30, in fact, we've been running on our new batteries for, you know, almost, you know, 15 years. And they still hold the charge. In fact, they hold a little bit more charge than they did in the beginning. Our guys are that good.
That's amazing.
And trying to do it. In fact, it's always funny because, you know, people will always say, are there life-limiting items on Hubble? You know, is there something getting close to its lifetime? The batteries are so far beyond their lifetimes. The battery experts just throw up their hands and they say, we have no idea how the Hubble guys are doing this on their batteries. No one should ever expect batteries to last as this long. And, you know, no one ever can. You can't build a spacecraft expecting your batteries to perform like Hubble's batteries perform.
Wow, that's for sure. Maybe it'll be blessed like the Voyagers. Maybe.
Yeah. Oh, yes. Yes. And so that's been, I mean, that's part of the, you know, the people on the ground have worked really, really hard. You know, we have a very, you know, unique thing. I mean, one of the things, I mean, there's so much I was going to show you guys. I mean, we actually have to worry about solar eclipses because Hubble can see solar eclipses in the sense that all of a sudden the sunlight will go away. And that's not good for us. We need that light during the daytime. So we actually have to plan for solar eclipses, even partial ones. We have to make sure there are some tests that we actually have to turn off of the telescope because the telescope is always checking itself to make sure everything's working. If all of a sudden it sees a power drop off the solar rays, it's going to think something's wrong and it's actually going to go into what's known as a safe mode. But so obviously, if you know a solar eclipse is coming, you don't want to do that. So we actually have to plan for solar eclipses. And I forgot, I had a graph I got from our electrical power guys showing the last solar eclipse. I mean, you can actually see it going through. You can see the solar eclipse happen. In fact, we see it for multiple orbits because we go through it multiple times.
Wow. Thank you.
You're welcome.
Mike, have you ever had an opportunity to do any observations yourself using the Hubble?
Yes, and now it's kind of funny because not to do science, although we've done these. I mean, there was the Kuiper Belt observation, but that was sort of using archival data. We were using old data that the FGSs had used. I actually have had, I mean, if you actually looked at, you know, what's Hubble looking at now at spacethelescopelive.org, if you did it at certain times, you actually would see my name on there because every once in a while we have to do tests. If we have a very important observation coming up, say, what was the interstellar asteroid, right? I can never say that right. But, you know, if you have an observation coming up that's critically important, that you need to make sure it's going to work the first time, that you want to make as best possible things. What we do is we'll test the guide stars out beforehand to make sure that they aren't doubles or there aren't any, you know, one's not fainter than the other ones or one's not an unknown variable. So we will actually schedule up observations that all we do is we point the telescope where we're going to be pointed, you know, next week. But we point and make sure, are these stars where we think they are? Are they this right brightness? And so those are my observations. And so I actually have, you know, like I said, I've actually gotten science. I've done the scientific discovery because of the Kuiper Belt project. And I find doubles all the time. I mean, the part of my job is figuring out why the guide stars don't work sometimes. And so I discover new double stars every week. But there will be some observations run with my name on it, though. And it's these tests. It's when we're testing out these guide stars or we're performing. We've done some specialized observing modes where we've had to do it. And I've put in observations where you can actually use defined guidance sensors as in science instruments. They can actually they used to do science. They did astrometry. They did very high precision measurement of positions of stars. And we actually will do those. If we're running a test of the telescope, I'll actually do observations of things like that. So yes, I have, which has always been a fun, you know, it's really fun to be able to see, you know, see my name. You know, people say, what's the telescope doing now? And someone will say, I don't know, it's doing something for Mike. He's doing something with the telescope.
How do you take flat fields?
How do we what?
Take flat fields.
They actually have a special mechanisms that they essentially, I mean, think of it as looking at an internal light source, you know, a white screen internally. They actually have mirrors that flop in that now direct the path internal to the instrument itself. And so it does flat fields that way. So a lot like you would, I mean, where, you know, well, I don't know how you do it, but I mean, a lot of the ground-based observatories will do, you know, they have these white screens they're looking at, or, you know, there's some sort of cover that's providing a uniform brightness. The instruments have it built into them so they can do internal flat fields.
Thanks.
Like, some people have asked about why this Hubble can't be serviced like from astronauts, by astronauts from the space station. Could you speak to that?
Yeah, the space station turns out it's too low. Can't get there from there. In fact, that was one of the neat things about the last Hubble servicing mission 4. And if you remember, there was a whole sorts of political hullabaloo about it. NASA didn't want to do it because they said it was too dangerous, because if you fly to Hubble, you cannot get to the space station with the shuttle. You can't get there from Hubble. You can't get to that orbit. And so vice versa, the space station guys can't get to the Hubble orbit. But during servicing mission 4, that was the problem. They said, you know, if there was a problem with the Hubble, this when they had the tiles, and they were, you know, saying if there's a problem with the orbiter, there's no way for us to get to the station. And that was why, for the only time in history, there were 2 space shuttles ready for launch on the pad. In fact, it's a beautiful picture. There's a beautiful picture of 2 space shuttles, ours, and then there was the backup one. That the only thing it was going to do was, it was the rescue vehicle, and they were both ready for launch at the same time. It was the only time NASA ever readied had 2 space shuttles ready to fly at the same time. But so that's why you can't do it from the space station. Now, it's an interesting question, and certainly there are some people who are asking this, is that if you think you can go to the moon and you think you can go to Mars, why can't you go back to Hubble and service it again? If you can't, if you come back and say that's too hard, we're going to go, it's too hard to service Hubble, and yet you think you can get to the moon and to the Mars? So there are actually people, you know, talking to the guys going, you know, you want to prove your spacecraft, go service Hubble. I mean, that's, you know, we did things on those servicing missions that people swore could never be done. And it was, you know, we proved so much servicing technology, so much the ability for humans to work into space. So there are people who are saying that. Now, you know, I think, you know, we're barking up a wrong tree. I mean, Hubble's getting old. People are willing to let it sort of, you know, gracefully age, although it's the most scientifically productive it's ever been. You can remember that graph I showed you at the beginning. There's more science coming out of Hubble today than ever, and it doesn't look like it's going to stop. And so, you know, Hubble is, you know, going to keep going. And hopefully, because we've gotten smart in these developing these new techniques for, you know, being able to run with 1 gyro, being able to run with 2 reaction wheels, we think we can keep going for a long time.
Are the gyros something that could be replaced?
Oh yeah, yeah. And we replace gyros all the time. Every single servicing mission up, we replace. And oh boy, the really, you know, you know, like, you know, you want stories, you know, the things you talk about when you're sitting around having beers, right? And it's like, you know, why didn't we replace the, you know, how come we actually have bad gyros, you know, and we actually have bad old gyros? Why didn't we replace them? They went up, there was gonna be replacing the gyros on the last servicing mission. That first little box slide I told you, yeah, they are plug and play. I mean, the gyros were made to be plug and play. That was something that was definitely, they knew they were gonna be replacing. Relatively easy to replace. Kind of hard to get to, but they have the special tools. They replaced one of them, no problem. Literally pull the, you know, undo a couple knobs, pull out the old one, slip the new one in, tighten it up, ready to go. Work fine. Go to do the second one, pull out the old one, slip the new one in. It won't work, slip the new one in. It won't engage, it won't engage, it won't engage, it won't engage. They spent, I mean, we spent a long time, and boy, EVA time is not something you want to burn. We burned, you know, 45 minutes having those guys do it, and the astronauts finally called down and said, it's not fitting, guys. You know, something's wrong. And it turns out, you know, this is, you know, someone on the ground hadn't actually done the check, the metrology check. The holes were not perfectly right for the bay they were trying to put it into. And so we didn't get 2 of the new gyros we wanted. And so we had to run with the old ones. But luckily we did get some new ones. And those some new ones that we have, the 3 gyros we have left, I talked about the flex leads, those really thin pieces of wire. We know why they were sort of corroding and decaying, and had to do with this fluid it was sitting in. They got a lot smarter. They were able to, when they built the new gyros for us, they used a different fluid, and our flex lead should not ever corrode anymore. Shouldn't, although one of them looks like it's having trouble, so we're sort of questioning that one. But so these new gyros should actually, they say they should never fail. So if I only need 1 gyro to operate Hubble, and I've got 3 that claim they'll never fail, I'm sitting in pretty good shape. So even though, like I said, we aren't totally believing they aren't going to fail, because we've actually had some scares lately. We have all of a sudden you have, if you have in fact, this just happened a couple of weeks ago. There was a motor current jump in one of the gyros. You don't want to see that, because if you put current through those flex leads, you're going to burn them. But so there's a motor current jump, and it's like now it's running at a lot higher current than it used to. It's like, okay. But that happens. They encounter little things in the fluid, and they have these jump up in currents. So yeah, but you'd love to, and we've thought of ways. Can you attach like an external gyro pack? Can you we've got this soft capture mechanism on the bottom. We know the spacecraft can go up and attach to it. Well, can't you just go up and attach a spacecraft there with gyros and sort of use those gyros? Trouble is getting the data to the computer. There is sort of think of it as a test port, a data test port, but it would be hard. You'd have to have some sort of robotic thing to be able to open up doors and unhook cables and plug in a new cable. And they've certainly the satellite servicing guys at Goddard have robotic capabilities. So they're certainly looking at it. But yeah, it'd be lovely to get new gyros. We would love to get new gyros.
Mike, based on your experience with the Hubble for so many years, do you have any opinion about the James Webb Telescope, in that you cannot service it and you cannot, upgrade it either? What do you have an opinion?
Yeah, and certainly that's sort of a design. That's something going into it, and you sort of design for that. I mean, there's obviously they build in a lot of redundancy, which Hubble also has a lot of redundancy. We actually have 3 computers, the same computer. We have 3 fine guidance. We had 6 gyros, and so certainly James Webb has a lot of redundancy built into it. I think they needed to get far enough out, because they're looking so far in the infrared. They couldn't be in a low Earth orbit. The telescope would not work in a low Earth orbit. So they, from the science point of view, they had to be where they are, and so they said, look, we can build, look at the Mars, the Mars missions. I mean, we know we can build hardware that lasts. And so you try to make things as simple as possible. You try to make it so you don't have a lot of moving parts. They don't have, the fine guidance sensors are, lots of moving parts, incredible machines. Luckily, they're still working. The James Webb uses, CCDs for guiding. I mean, no moving parts, as long, and they've got multiple, backup electronics. So they did it by design, and they had to do it for the science. James Webb is going, it's going to give you very, very deep, and out there. And so that was the decision they made, and it should all work. I mean, we've gotten really good. They learned a lot from Hubble, of how to build things, and how to make them so they last. So it was a design thing. So hopefully it lasts a nice long time, although it is cryogenic. The weird thing is James Webb has a lifetime, and it has to do with the cryogenics. They're operating those things so cold, they actually do have cryogenic reservoirs that will eventually end up. So, depending on how long Hubble lasts, Hubble could outlast the Webb telescope. They don't think so, but we like to think so.
Mike, you mentioned Hubble is in low Earth orbit. Is there any issue with atmospheric drag where it is?
Yeah, and certainly we were really glad to get rid of the big solar arrays, because those were acting like sails. The smaller arrays actually reduced that drag, which was good. We are also very sensitive to during periods of high solar activity, the atmosphere puffs out, right? And so we get higher drag. And so the fact, as you know, Steve, There's not been a lot of solar activity lately. I mean, it's been kind of a bad minimum, which is actually great for Hubble because we haven't been going down. In fact, we know that we get predictions of when Hubble should re-enter, and those keep getting pushed out. Currently, I think it's 2035 or at the absolute earliest, and that's only if you actually have solar maximums that peak out at the most max you've ever had, which is not going to happen from what I'm seeing. So yes, it is. We do have that drag, and we actually have enough of a drag from that, which is why they have to do something about it. I mean, if they could push us up high enough, we'd be out of the drag and we'd stay there forever. But that's why they have to do something. There will be another mission to Hubble at the end.
Is there
Mike, has there ever been any problems caused by solar flares? I mean, over the past 30-something years, we've had at least one good maximum.
Yeah, and we certainly have what we call a bit flips occur on the instrumentation. I mean, space is a rough environment, and we are not. One of the first pictures I showed where things were located in a telescope, there was something called the equipment section. It's hanging on the outside edge of the telescope. We actually have some electronics equipment in there, which is, it's seeing a lot of the hard radiation coming from space. And yeah, we have actually identified these bit flip anomalies. So what happens is the computer will be going along and all of a sudden a bit will be flipped in one of the commands and it just makes the computer freak out. The computer says, what's this? Or it makes the computer do something it wasn't supposed to do, which is even more bothersome. And we've had those things happen when there's been no reason to happen, but we've actually correlated them with high intensity levels of solar activity. So yeah, if the sun gets really, really active, we have to be a little more, every once in a while we'll have like one of our instruments will trip and they'll say something's wrong with this command. Well, that's because, 0 was turned into 1 or a 1 was turned into 0. And all of a sudden, the checksums don't work. And so yeah, we've actually correlated it with some. I mean, we've actually had certain events where, they'll say, oh, well, we're going to have nice auroras and stuff like this, because the particles are hitting the Earth. It's like, well, that's, so we got to be on our toes because if something happens, we'll go, yeah, okay, it's a particle hit from the radiation. Luckily, I mean, it's sort of made it, although that's sort of another thing. We have a lot of equipment on Hubble that is so far past its lifetime in terms of radiation exposure. I mean, there's in fact, unfortunately, the fine guidance sensors, the things that are critical to pointing Hubble, there are two pieces. There's the optical piece, which is the FGS, and then there's the fine guidance electronics, which are, think of it as the computer, although it's so old and so hardly a computer at all, but it's what runs it. It's like as a computer. The computers have been in space for so long, because those have never been replaced. They have been in space so long, they are like, 10 times beyond their life expectancy in terms of the radiation exposure. So, we're expecting, if one of those failed, we'd go, well, okay, that's not a surprise, people, because it's so hard. So it's a tough environment. I mean, and that's why, part of the reason Hubble is still up and still doing what it does is so amazing. People look at Hubble and go, how in the world are you guys still running that telescope?
Is there a replacement
for
for
question.
Hubble in the works?
Is there a what?
A replacement for Hubble in the works or on the drawing board?
If you guys have heard about the Nancy Grace Roman Space Telescope, it's another telescope, and I know one of you guys, Steve, knows the story behind, the reason we could fly Hubble and the reason we knew that Hubble would work is because Hubble is not the only 2.4 meter telescope up in space. But there's actually, it's the only one that's looking out. There are a bunch of them looking down that can actually focus down. It was actually, there was a spy satellite program that essentially where the Hubble mirror, they knew Hubble would work because these spy satellites work. They made some mirrors for them and they had one extra left over and it got declassified and they actually gave this mirror to somebody. So it's a Hubble size mirror. And they gave it and they're building a telescope around it. It's going to be a wide field infrared a telescope, but wide field. I mean, Hubble, not very wide field. I mean, and certainly Webb is not very wide field. But this is not really a replacement because once again, this is just going to be in infrared. no one can do the ultraviolet. There's no replacement for the ultraviolet capability of Hubble, and there's no replacement for the visible capability of Hubble. Everyone's jumping on because of the scientifically, the infrared is actually an interesting place to look. I mean, Webb is going to answer some specific questions, but no, the ultraviolet, there is no replacement for Hubble. And unfortunately, you look at some of the more recent cool stuff coming off of Hubble, the exoplanet observations, the detection of the salt water ocean underneath on Ganymede, that's ultraviolet. That's using the ultraviolet stuff. So it's a shame, which is why they want to keep Hubble going. I mean, we got to keep Hubble going because it's the only game in town for ultraviolet.
You talked in one of your videos about the deep field work that was done. Can you touch on that a little bit about what needed to be done from a control aspect to get those pictures?
Yeah, the Hubble deep field, and there's been multiple deep fields. And in fact, if you pay really close attention to what I say in the video, there's a thing where you go, wait a minute, that doesn't make sense. It's because there's been the Hubble deep field, there's been the Hubble ultra deep field, and then there's been the Hubble extreme deep field. And the idea is that you take use of these, you take advantage of these things, the continuous viewing zones, and you point the telescope and you just keep it pointed. Well, the telescope was not made to do that. And the reason it's not made to do that is telescopes up in space, half the time we're in sunlight. Sunlight gets the telescope extremely hot on the outer edges. In fact, we have to make sure that there's no sunlight coming into the baffle at all, even at a very small angle, because if the sunlight was to hit the paint on the inner side of the baffle, it boils it off. I mean, the sunlight is so hard. And so the telescope, half the telescope is getting baked, and the other half is seeing deep space cold. So think of the mechanical stress is going on. The telescope is made to be perfectly straight when it sort of is stressed like that, when half of it is hot and half of it is cold. And it's assuming you're sort of moving things around. If you stare at the same spot in the sky all the time, you've only got the sun shining on one specific part of the telescope all the time. And so the telescope, it actually flexes, it bends a little bit, and you have to take that into account. And also the FGSs, they don't like to not move very much. The FGSs, when they're tracking the stars, they're just sort of jittering they're going at a very, very small pace. They're hardly moving at all. And so the mechanism sort of gets sticky, if you will. They don't have a chance where normally they're moving around a lot and the bearings are able to turn this way and turn that way, and you're sort of redistributing your lubrication. So you had to worry about that. The other bit was the science data. I mean, we don't have a lot of storage capability. We've got solid state recorders, and I know, I just bought my daughter laptop. It has a 500 gigabyte solid state drive, right? 500 gigabyte. The Hubble Space Telescope's solid state drive are 11 gigabits, essentially 1.4 gigabyte. Those are our big solid state drives. We don't have a lot of storage capacity here. So if you're staring at the same spot in space, and these cameras chunk out a lot of data. I mean, I know there's a bunch of you guys doing imaging. You know how much, disk space images take. Well, okay, the instruments have their own internal storage capabilities, which are actually much more than Hubble's. They can store the pictures, and we compress the heck out of them. Obviously, it's lossless compression, but we still compress the heck out of them. Most of it's black background anyway, right? So you can get good compression, but you still have to get all that data through the telescope communications down to the ground. In the teeter satellites, we can only see them maybe 20 minutes in orbit. And so yeah, it's really hard to do these really long observations, and it had to be planned for a long time. We had to do thermal studies, we had to do power studies. The power guys were going, wait a minute, we don't want to keep the rays like that all the time. And so it was kind of hard, but I think the science return was wonderful for it, because the science coming out of the deep fields, was just phenomenal. It was actually a really bold move when it was one of the directors of this institute who said, he had all this director's discretionary time, DDR. He said, I want to look at a blank spot of sky. They're going, why? It's like, I want to see what's there. Talk about exploration. And boy, did it pay off. It had to be one of Hubble's, enduring legacies is the deep field. And the deep field, and they kept pushing it. They kept going back to it and kept adding, because it's CCDs. You can just keep adding on, right? That's how you get to the extreme, and the ultra deep field and the extreme deep field where you start doing infrared. And this allowed Hubble to push back how far it could see. And when you're talking about James Webb, the whole idea behind James Webb was it was going to be able to see in the infrared and look far back in time. And they said, look, when Hubble can look this far back in time. Well, that was what Hubble was originally designed to look at, that far back in time. That was before we got really smart. And they said, so Hubble can look this far back in time. James Webb, can look. You guys can't see it, but I'm spreading my arms out. Well, James Webb can look this far back in time. And so they said, that's why we need James Webb. Well, Hubble starts doing these ultra deep fields, and Hubble gets pushing back further and further and further back in time until we're getting really close to the ionization boundary. And then, the Webb guys are going, stop it. That was for us. You guys can't look back that far. And we're going, well, our science guys, they had some time on their hands. They figured out a way to do it. So we've been actually pushing it back, very, very far. And so those deep fields, yeah, they take, we have to think about them long and hard. There are other types of observations that we have to plan for. Hubble has observed the moon on a couple occasions. The moon is really hard to observe. One, it's so close. Two, it moves so fast. And three, we are spinning around the Earth. The moon is spinning around the Earth. The moon's motion to Hubble is not linear at all. And you have to figure out how to observe. And it's hard actually to catch the moon. And one time we actually missed. But we have, those observations take a lot of prep time. Anything special, like for these special comets, these close coming in comets. Sometimes if we're looking at a comet that's really close, it's moving so fast, the fine guidance sensors can't move fast enough to track it. We actually just have to let Hubble run on the gyros alone, which it can do. And if you're doing a picture, it's probably pretty good enough. And so, sometimes we have to plan those things. So probably a lot more information than you.
One last question. Is there any possible way that the telescope could be put in a synchronous orbit around the Earth to stay continuously in the shadow of the Earth?
No, it's just there's no way for us to get up that high. There's no vehicle. I mean, you could, if you have, at the end when you send up the spacecraft to attach to the bottom of it, you could push it up so it is in a synchronous orbit. I mean, that's what, 24,000 miles? And so you could do that, but it's but it's not.
I didn't realize the synchronous orbit required such a high elevation from the Earth.
Yeah.
Okay.
Well, it'd have to be a 24-hour orbit to stay in the night side, I guess.
Yeah, and right now we're 90 minutes, so you got to be way out there.
Yeah, that's right. Thank you.
Mike, it occurs to me that you got to be one of the luckiest guys in astronomy to have such a great job. And I'm just wondering, are any parts of your job really challenging anymore, or has it gotten routine after all these years?
One of the things I really like, and I've talked to you, I just talked to you about this, Richard. I mean, I love my job. I mean, maybe you guys can see that. I really like my job. And it's part of the reason is because it is so fascinating. You would think that after 28 years, I would know everything there is to know about Hubble. Absolutely not. I mean, there are still things I'm still learning at. And there are still things we do trying to develop these new modes. I mean, the science guys are always coming up with these great things. In a recent example of this is the exoplanet stuff. When Hubble was launched, there were no exoplanets known. Hubble was never designed to observe exoplanets. Hubble was never thought to be able to observe exoplanets. It's only a 2.4 meter telescope. It could never observe planets. Even when the first exoplanets were found, no one said, Hubble can't contribute anything about this. But then our science guys came back and they said, if you can make the telescope move in this very particular way, essentially we move this telescope scan back and forth very, very accurately. They say we can actually use some of the imaging instruments we have, the CCD cameras, and because of the way we can reduce the data, we can get this incredible information from these exoplanets. And so we had to develop whole new software modes of figuring out how to control the telescope so it would do these very particular motions. And then, so you have to develop it, you have to figure out how to do software, develop it, put it in tests, and you have to test the heck out of it because you don't want to end up in front of Congress. and then you put it up there, and then you always have to change it. And so it is constantly changing. I mean, one of the neat things I get to do is I deal a lot with anomalies in terms of when things don't go wrong. I'm the one who's told about it. And I always like to tell people, I mean, when Hubble's 300 miles up in orbit, right, going around the Earth, doing its business. If something goes wrong on Hubble, if it says, wait a minute, this isn't right, Hubble pages me. I mean, my phone is the first phone to go off. I'm the first one to know something's not right. The telescope's, sending down a message saying, hey, something's not right. Figure out what it is. It's like, oh my gosh. And so, you got to get up, you got to fire up the computer, you got to figure out, you got to hook up to the telemetry, which we can actually do, all remotely now. And we have to look at it. And we have to say, what happened here? What do I see now? How do I go back? I mean, I have to play, it's almost like, solving little murder mysteries, who killed this guy star? Why didn't this guy work? What is it about this that's making it not work? And so it's even more challenging now. As Hubble ages, it gets more and more challenging because we are dealing with more and more problems of that. Like I said, one of the gyros we have left is real pain in the butt. He has an amazing weird signature that's driving us nuts. We're able to get the science out. In fact, if you ask the science guys, they're going, oh yeah, Hubble's perfectly fine. And we're going, man, we are having to work our butts off just to get you guys that science. This is not working right the way it's supposed to be, but it's not, the bottom line is as long as you don't affect the science, it's good. I mean, that's the idea. The scientists shouldn't know that you had trouble. So we have to build ways into where we can get around this trouble. We know, oh, it's going to have to do it twice. For whatever reason, it has to do it twice before it's going to get it. So we build that into the system. And so we're constantly changing things. I mean, we rewrite the flight software is constantly being updated. In fact, we've got a big update coming out in February, which is, it's sort of strange to see because you think of, it's 28 years. Why are you guys changing the flight software for Hubble? It's like, we're adding new capabilities. We're putting in new things to be able to do. It's amazing how interesting it keeps going. I mean, it is just so fascinating. It's because it's fun being on the front lines of having to work it. Like I said, if something goes wrong, there's me and there's 4 or 5 other guys. We're talking on the phone at 2 a.m. going, how are we going to fix this? And it's like, oh, call Jerry. We got to send Jerry into the Goddard. You got to wake poor Jerry up. Jerry's got to drive his butt down in the Goddard, get onto the base, fire up the computers down there, and make sure he can talk to the telescope, send the commands back and forth. And we tell Jerry, okay, now send this one. He'll be sad because we'll say, send this one command. And Jerry sends the command. And we go, perfect, great, go home now. And he's got to put everything back to bed and he drives back home. So it's a lot of fun.
Just saw Tango go out. Tired of listening to you?
Yeah.
Just a couple. It's almost 9 o'clock. If there's 1 or 2 more questions.
I have a question I'd like to ask. I've been using the GuideStar catalog for about 20 years. It's part of the control system for my remote operation of the telescope. As far as I can remember, it's only been through like a couple of iterations, changes and updates. Are you still updating the GuideStar catalog, or are you using more complete astrometric catalogs now?
Oh, wow. Excellent question. It's so fun to talk to guys who like you who know what they're talking about. Yeah, good point. We are updating the GuideStar catalog. What we're using is we're using the Gaia coordinates, the Gaia magnitudes, and the Gaia proper motions in associating them with the Hubble stars. And so, I mean, the fine guidance sensors can only they can only track down to about 14th magnitude. So it's not like, there are a lot of stars, but not as many as 20th magnitude stars. And so there is a Hubble GuideStar catalog. We're coming out with a new version that we use for Hubble called, it's 2.4.2. So yeah, there is a new one being released. And what it is we've essentially taken all the Hubble guide stars. We found their information in the Gaia catalog, because the Gaia catalog has the absolutely best, it's Gaia, guys. If you don't know about the Gaia mission, that's a wonderful, incredible mission. It's got the best positions, the best magnitudes, and the best proper motions of the star. And so we've just put all that data onto our GuideStar catalog. So yes, we are constantly updating our GuideStar catalog. And whenever I find these doubles, all that, I do about once or twice a week. We have to take those out of the catalog, although technically we don't take them out. We just got a super list that's run at the end saying you can't use this star because we know it's a double. So yeah, it is. We are updating it now. I don't know. You must be able to get it somewhere. So, but there will be a new one released. In fact, it's released. We just started using it last week, and so it's 242. It's the latest one we started using. So yeah. Good
One
question.
of the problems I have is that certain areas of the sky, there are not enough stars in that area for it to lock on to. And I have to manually move the scope to some area of the sky in order for there to be enough matching stars to the guide star catalog. So is there a star density change?
No, because I mean, that's just, there are areas of the sky. In fact, Hubble has that same problem. There are actually areas of the sky where I said we need to have two, we have to have two defined guidance sensors to lock onto the star to control it. Well, sometimes there's just no stars. We can get a star in one of them, but you can't find any stars in the other ones. There aren't enough bright ones. I mean, the trouble is we've got like a 14.5 magnitude limit. And so there are times when we actually can only use one FGS guider just because of that. And so no, that's a problem even Hubble has, is there are parts of the sky where we can't find guide stars either. And so we actually have to do this trick of what we do is like you said, what they'll do is they'll move it a little bit. We can actually do a funky thing where we can roll the telescope around, where you're pointed. We can actually, because we're floating in space, we can actually take our entire telescope and roll it so that, we can move where the FGSs are looking. So usually we can roll it to at least get one. I don't think there's ever been any spots where we haven't found anything to guide on. Although even if that was the case, we can just do this gyro guiding. Depending, we can't do big science there, but you can do some science. But yeah, no. So our telescope has the same problem as your telescope. That's just star skies. They're just regions of the sky that don't have any bright stars. And bright being 13th magnitude or so.
Okay, it's 9 o'clock. I think this has been really wonderful. But I think it's time that we're starting to have some people drop off. So I think it's time that we, unfortunately, wrap it up. But I really want to thank you, Mike. Your enthusiasm really does come through. It's obvious how much you enjoy this. And I've really enjoyed it, and I'm sure everybody else did too. We had a good crowd, and we didn't have too many people drop out, so that's always good. So I want to thank you again, and please send me a picture of that focuser attachment. You know what I'm talking about.
Yeah, I know what you're talking about. Yeah, I'll get to that.